Hi, welcome to lesson 3 in the series of digital signal processing using MATLAB and Python. You can also visit us at www.jcbrolabs.org and you can also download the documents which we have used in this video from our website in the download section. So in this lesson we will talk about digital systems and what are the various kinds of digital system, and we'll give an intro of LTI system, that is very famous and implementable system which is generally used for most of the applications, and then we will drive the stability condition for the systems. So let's start with So today's lecture will be on digital system. So prior to going through this digital system, we will do some important concept which was related to sequences, like how to represent a digital sequence. So I hope you remember the that one impulse response representation, that is known as the delta n, or the impulse signal, that is delta n. It exists only at n equals to 0. So representation of digital sequence. Suppose we have a sequence x of n as like -1, 2, and then 1, and then 2, and so, and let's say this is the index 0 and index -1, 1, 2, right? So we can also represent this sequence in the graphical form which you are familiar with. If this is the index n, then we can simply represent at n equals to 0 the value of this one is 2, and at equals to -1 the value of this one is -1, and at index 1 the value of it is as 1, at and index 2 value of the signal is 2. So there is one form of representation of this digital sequence, but if someone asks like how to represent this sequence in a form of a mathematical expression, so then we can write a sequence or discrete sequence in a form of the shifted version of the impulse signal. That means this -1 can be represented at -1 into del of n plus 1, and then plus 2 it can be represented as delta of n, plus this 1 can be represented as 1 into del of n minus 1, and then plus this 2 can be represented as del of n minus 2. So this is the basic information which you should need to know, like any sequence or a digital number can be represented as a shifted version of the impulse signal, and I am sure you may be familiar with this shifted version. If I am writing delta n minus 1, that means a delta signal exists at n equals to 1 only. Okay, so this is basic of the signal sense system. So now let's move forward, because this representation is also important because it may be required in the upcoming videos for understanding of some of the basic concepts. Okay, so now let's move with the digital systems or the discrete systems. We can say it digital, or because as we discussed both these terms move side by side, discrete systems. So if I ask you the definition of the system, so you may be familiar with the basic definition. A system is nothing but a combination of some component connected in such a way that they change the input or to some form of the required output, right? So if we have a digital system, obviously a combination of some of the components, then we apply input, that is x of n, at one side, and then we get the output y of n at the outside as the output. So this y of n is known as the output, and this system changes or transforms the input signal, applies to it in the form of a required one. So yn can be said as a function of some input sequence, right? So ultimately it transforms the inputs and then gives to the output. So there are certain terminologies, or we think about the system examples, then we can think of a bike. So in a bike, your input is the throttle input, right? And with respect to it, you will get a speed. So your speed is the output, or the distance traveled is the output. Similarly, if we talk about a fan, in fan your input is a switch pressing and output is your air, how much or at what speed your fan is revolving. If we talk about a system like a microphone, so input is your vibrations or sound vibration, which for example I am speaking, and the output is the corresponding electrical signal, filtered electrical signal, because ultimately microphone is a combination of components like filters and some discrete components and some transducer and also. Okay, so let's move forward. Alright, in a form of digital sequence, so there are certain terminologies to the input. Let's say if we apply xn, and this is the input signal, and there are some standard formats. If xn is equals to a delta n, that is the impulse signal, then yn is known as the impulse response. Right? So we are applying input as a impulse signal, then the output we will get, that will be a impulse response. Similarly, if we apply as x of n as u of n, which is the step signal or a unit step signal, then yn is the step response. So these two terms are very famous with respect to, you can think of a control system as well, or several other systems as well, like what is the response of the system. So yn is a step response. Someone is saying yn is a step response, that means input is a step signal. If someone is asking what is the impulse response, that means the input is the impulse signal. And this is more important because it represents entirely the system characteristics. This represents the entirely system characteristics, and it also can be represented in the form of h of n, which also generally represented in the form of h of n. So this impulse response is also termed as h of n. So let's move forward. The simple digital system example is like accumulator, if we say it. So what does accumulator does? It simply keeps recording the previous values of input. Let's say if I write it, y of n is equals to l equals to minus infinity to n x of l. Okay, so we can further think about this accumulator as, let's say y of n is equals to, if we write like l equals to minus infinity to n minus 1 and then plus nth term. So this can be further like it is a previous combination, y of n minus 1 plus x of n. So this accumulator we can write it in the form of this y of n as y of n minus 1 plus x of n. So this form of representation of systems is known as the difference equations. Similarly, if you may be familiar with the time domain representation of the system, then system can be represented with the differential equations, right? Similarly, in digital domain, the system can be represented in a form of difference equations. Okay, so difference equation is nothing but a combination of shifted version of previous output or previous input with respect to the present. So present output of the yn depends on the previous output plus present input. So a simplest representation of a system, right? So now we can move forward. There are several classification of the digital systems like static or dynamic system, causal, non-causal system, linear, non-linear system, time invariant, time varying system, stable system, unstable system, FIR systems or IR system. But we will be dealing with some of the important ones which will be required in future as well. So when we first classification is a linear system or a non-linear system. So I hope or I am sure you may be familiar with it. So a system is said to be a linear if it follows the property of superpositions, right? Superposition means if x of n is a combination, suppose x of n, if we apply to system, it gives output to the y of n, and if x to n is applied as the input and it gives output as y to n. And now suppose we applied a weighted sum of these two inputs, let's say a times x1s plus b times x2n. So our output should also be like a times y1n plus b times y2n. So if any system follows this property, the property of this superposition, then our system is said to be a linear system. And if some system doesn't follow this property, that system is said to be a non-linear system, right? So in practice we generally require this linear system, but all the systems are not linear. Some systems are non-linear as well, which are very useful to us. So similarly, another one is the property is that shift invariant, or generally known as the time invariant or time invariance system. So a shift invariant system, suppose we applied an input to the system, it gives output to as y of n, and if we apply a shifted version of it, shifted version means x of n minus n0, right? So y output should also be shifted by the same amount, right? If some system follows this kind of property, then that system is said to be a shift invariant or the time invariant system, right? So time invariant system, think about a case. Suppose you want to turn on the fan right now, and it is giving the correct output in terms of the speed. Even if you press the switch again after 1 hour, it will give you similar output after 1 hour, right? So in that case, your fan is a kind of time invariant system. And think about the time invariant system. Suppose fan could be a time varying system. That means if you press press input right now, right, say, and fan is revolving at 200 rpm, and suppose after 1 hour it starts revolving at 300 rpm for the same input, then you will be saying, okay, this system has become a time invariant. And such systems could be very dangerous, or they could not be used for any practical purpose. So generally our system needs to be time invariant, so it should not change the output with respect to time. Similarly, third condition is very special condition, and that is known as the special type of system, that is known as the stable system. Obviously we all know that all systems should be stable. So stable system means if the output is stable, or it is not we have applied some input and it is not going beyond certain limits, only then we will say the system is stable. So one of the famous condition for this stable system is known as the BIBO stability. BIBO stability means bounded input and bounded output. That means bounded input, bounded output. Bounded input means and bounded output means if we are applying to a system a bounded input signal. So bounded input means your signal is absolute summable, right? Or it remains within the specified limit. So bounded input means x of n is less than some value mx, which is less than infinity. Okay, like a signal, this one, a step signal. So it is a bounded input signal. Similarly, for bounded input, if your output is also bounded, right? So bounded output means your output should also be less than some any value, say by, and less than infinity. Let's say output is going like this. So in this case output is also bounded, right? So for this kind of system input, if output is bounded, then we will say okay, our system is a BIBO stable. If we are not getting such kind of output, and output, suppose we apply this signal and output goes like this, then we will say okay, output is going beyond its limits and the system will not be termed as a stable system. Okay, so based on these two criteria, mainly time invariant and the linear system, there is a special class of system which are linear time invariant system. Linear time invariant, and this is the broad category of system which we study in this subject, linear time invariant systems, or also known as the LTI systems. So LTI systems are both linear as well as time invariant, right? So we say any system as the time invariant for an LTI system. Let's say it is an LTI system and it is the y of n is the output and this x of n is the input, right? So it represents, let's say h of n is the impulse response of the system for an LTI system. H of n is the impulse response. So these systems are very easy to design and analyze. That is why we tried that our system should be an LTI system. So in this case, for this LTI system, input output relationship is simple, like y of n is equals to xn convolution with, so this sign, let's say, represents a convolution sign, and h of n, or this h of convolution can also be written as like either h of n convolved with x of n. So output of this LTI system can be given by this particular equation, and I hope you are familiar with this convolution. So if we represent it, if we further expand it, it can be written as summation of, let's say, k equals to minus infinite to infinite x of k into h of n minus k, right? Or it can also be written as either k equals to minus infinity to infinity h of k into x of n minus k. So this is the formula for convolution as well as the output of the an LTI system. So from here it is clear, if some LTI system is there and it has been defined by its impulse response h of n, then the output will be given by xn convolution with h of n, and obviously in discrete time domain. Okay, we will further learn about it when we will be dealing with this Z transform. Okay, so there is a special category or general terms which is used for related to the stability of an LTI system. So let's talk about stability of a LTI system, of an LTI systems, or in terms of h of n, like what is the stability condition in terms of h of n. So we know this x of n was like summation of k equals to minus infinity to infinity h of k into x of, let's say, n minus k. We will keep on simple. So in order to be a stable system, this mode of yn, right, should be less than the infinity, as we discussed just earlier. So if we put this yn value here, and that is k of minus infinity to infinity, so it will be a kind of like we are taking the mode of this one, h of k into x of n minus k, and which can be written as like summation of k equals to minus infinity to infinity mod of h of k into mod of x of n minus k, and this should be less than infinity. Now we also know this value, like mod of x of n minus k is x of n minus k is at max or less than suppose b of x, because it is a bounded input, right? Because stability will be treated when input is bounded, only then output is bounded. So obviously our input is bounded for making a system to be stable, so this value is less than b of x. So we can write simply like b of x into summation of k equals to minus infinity to infinity mod of h of k should be less than infinity, and it leads to the condition like this h of n. So it leads to this condition for stability like h of k, or we can represent k by n, let's say n equals to minus infinity to infinity mod of h of n, it should be less than infinity, right? So this is the condition of BIBO stable condition. So what does exactly this represent? So it says like our system will be stable, only if and only if impulse response of the system is absolute summable. So this is a condition of absolute summability. That means if we sum any sequence from minus infinity to infinity, it turns out to be less than infinite, right? So this was the introduction of the system, and in our upcoming videos we will stop here for today. It will give you some time to understand some of these basic concepts. Okay, so we'll stop here, and I hope you understand some of the basic concepts of digital systems, and what is the meaning of LTI system, and what is the condition for stability of an LTI system, and what is the condition of absolute summability. So if you have any doubt or any suggestion with respect to this video lecture, you can let us know by commenting below on this video, and further you can subscribe to our channel in order to help us for making these free online videos. So I hope you understand it. So that's it for this video. Thank you.